Welcome back. A membership table is another way of proving set identities. Here is an example. You want to show that A intersection B union A intersection C is this. A intersection B union C. Notice how the distribution goes through. This column must be equal to this column. That's the idea. So what do these columns represent? So here are three sets A, B, C. If you have an element, one represents membership of the element in your set. So pretend you have an element which is in A and in B and in C. Then it is in B union C because it's in B and C. So it's in the union. It's also in A, so it is in the intersection of A with B union C. Now, based on this, is it in A and B? Yes. Is it in A and C? Yes. So is it in A and B union A and C? Yes. So you see, membership is represented by 1. Lack of membership is represented by 0. That is, here is an element which is in A and B but not in C. Question is it in B union C? Well, it is in B, therefore it is in B union C. Is it in A intersection B union C? Yes, it is in A and in B union C, therefore it is in the intersection. Question, A intersection B? Yes, it's in both A and B. A intersection C? No, because it is not in C, so it is not in A intersection C. What about union of A intersection B and A intersection C? Union. It is in A intersection B, therefore it is in the union. So you get a 1 here. So you see, this is one way of proving identities. It's a beautiful way because it is all compact. Eventually, you're comparing this column with this column. If they are identical, then that set is equal to this set. So the issue is to fill in all possible values, all possible ways of arranging ones and zeros among these three sets. Okay, so you might want to try a few set identities using membership tables. All right. Generalized unions and intersections. Note that the binary operation of union is associative. In other words, A union B, union C is same as first you take union of B and C and then union it with A. So because of associativity, we may as well write it without parenthesis. It doesn't matter which place you put the parenthesis. So A union B union C without parenthesis is acceptable. Likewise, binary operation of intersection is associative. So we may write it without parenthesis. Here are the Venn diagrams representing union of three sets, intersection of three sets. Now, so you might want to try using certain examples. It's not a new material. We can proceed. The union of a collection of sets, say not just 2 or 3, say you have more sets. It's written in this fashion. Parenthesis is not required because union is associative. So A1 union, A2 union, so on, all the way to AN is written with a common union, I going from 1 to n of AI. If you have infinitely many sets, then you write it with a common union, I going from 1 to infinity. Likewise, intersection of a collection of sets is the set that contains those elements that are members of all the sets in the collections. Okay, we may use the following notation. Instead of writing intersection several times, you simply write it once, I going from 1 to n. In the case of an infinite collection, you write it once, I going from 1 to infinity. Okay. So now you might want to try this exercise. Countably infinite family of sets, find its union. Countably infinite family of sets, find its intersection. The last subtopic is computer representation of sets. Assume that the universal set U is finite. Specify an arbitrary ordering of the elements of U. Since you have a finite set, it's easy to do. Choose some arbitrary ordering. For any subset A of U, we assign a binary string of length cardinality U. Ith bit in this string is 1 if the ith element is an A, 0 otherwise. Now use V for union and conjunction for intersection. Complement is simply reversing all the zeros by 1 and all the ones by 0. Construct a concrete example. So this would be nice to see. We have example here. So you have a finite universal set. A is this set 1, 2, 3, 4, 5. We have already ordered U. So here is how you would say. As a string, a binary string, okay, the first element is present. The second element is present. The third element is present. The fourth element is present. Fifth element is present. 6 onwards, it's not present. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the binary string for A. Here, the binary string for B is, the first one is absent, second one is present, third one is present, fourth one is absent, fifth one is present, sixth one is absent, seventh one is present, eighth one is present, ninth one is present, 10, 11, 12, 13, 14, 15 are absent. So I hope you understood how I matched it, right? So 1 is present, so the first digit is present. 1 is absent in B, so the first digit is 0. All right. Now let's look at A union B. Okay. I'm going to take this string and take the disjunction with this string. All right. Disjunction means 1 or 0. All right. 1 or 0, let me align it. So 1 or 0 is 1, 1 or 1 is 1, 1 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1, 0 or 0 is a 0, 0 or 1 is 1, 0 or 1 is 1, 0 or 1 is 1. The rest are all zeros. 1, 0, 0, 0, 0, 0, 0. That is A union B. What does that mean? So the first digit is present. The first digit represents presence of 1. Okay. Second digit represents presence of 2. Third one represents, this is getting shaken. All right. So here 1 is present, 2 is present, 3 is present, 4 is present, 1, 2, 3, 4, 5 is present, 6 is absent, 7 is present, 8 is present, 9 is present, and everybody else is absent. So that should be A union B. Is that the case? Let's see. A 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 5 have already been written, 7, 8, 9. That's it. So you see, we use bit operations. So this, for union, we use disjunction. Okay. Disjunction. Likewise, for intersection, what do we do for intersection? You are going to use conjunction here. So 1 and 0 is 0, 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0, then 1 and 1 is 1, 0 and 0 is 0, everybody else is 0 because there are a bunch of zeros, so everything else is a 0. So we have used conjunction. All right. Let's see what it means for the set. Well, the first one is not present, second one is present, 2 is present, then 3 is present, 4 is not present, 5 is present, and nothing else is present. Look for commonality. That's what intersection represents. 2, 3, 5, and nothing else is common. So this is a way to use strings, binary bit strings, to compute unions and intersections. All right. So this is a programmable approach. You see, this is a programmable approach, and therefore it is quite useful. Okay. So that completes lesson 8. Next videos will cover lesson 9. Until then,